Africa Flores!
Muchas gracias. Hello, how is everyone? ¿Cómo está Porto Alegre hoy? Now you can hear me? Yeah, perfect, perfect. So I was saying that when you think about NASA, you may be thinking about astronauts, other planets, but my talk won't be about that. I will focus on planet Earth because NASA has been monitoring the Earth for the longest. We have multiple missions that are constantly taking measurements that are very consistent of our planet. And this is what allows us to understand what is going on and how the weather is changing, what are the impacts of climate change. Currently, we have multiple missions on orbit that are collecting data of our planet at different parts of the electromagnetic spectrum. This is just a snapshot of the current satellites that are on orbit that are constantly monitoring our Earth. Many of those missions are created in collaboration with other space agencies. And this is what allows us to monitor what is going on over the ocean, in the atmosphere. We can measure precipitation. We can measure when there are the clouds. We have become very good at forecast weather, for example, and also to understand the impacts that humans have on climate change, and to see how things are changing right now and how that compares with the history. And something that is unique about this data is that it's consistent, and the measurements are available since the 70s and even way back, and we can do this time series analysis that gives us a whole picture of our whole planet. But one thing about the data, for example, that we are visualizing right now is that this is very coarse spatial resolution, and usually it's about 5 kilometers, 1 kilometer. So when we try to understand what is going on in our country, or at a regional scale, at a local scale, at our city, it provides information, but maybe not at the scale that we needed. But all of that changed in 2008 when the N.A.S.A archive was open to the public. So this data has always been open to the public, and everyone can go and use it and process it. And if you are very interested on data, please visit the multiple NASA websites where you can download this data for free. But in 2008, the N.A.S.A archive was open. This is a 30-meter resolution data set that allows us to answer questions at a smaller scale. And this is the kind of stuff that we can do with satellite data at higher spatial resolution that is freely available. And here we are monitoring algae blooms in my home country, Guatemala. And I like to say that I have no bias, but this is one of the most beautiful lakes in the world. Not because I was born there, but it is. It's surrounded by volcanoes, and it's very well known for the transparency of its waters. But since 2009, it started suffering algae blooms. And using a multi-sensor approach with this higher spatial resolution data, we are able to monitor, in this case, water quality. But this is not the only thing that we can do. We can monitor forests, we can monitor agriculture, different crops, how things are changing. And because N.A.S.A has been available since the 1970s, we have over 5 decades of data. And that's unique, and that's a lot of data. And let me see here. And something that this has allowed us is to do analysis that is not only in space and using different spectral resolutions that solve for these different issues, but we can also look through time. And in addition, so what we do with satellite data is monitor. And I know that the applications of satellite data go way beyond environmental analysis, but I focus on environmental analysis. That's my background. I study agronomy with focus on natural resources. And I think that the biodiversity community, the ecosystem community has been using satellite data for a long period of time because it's very difficult to do this, to have this type of measurements in situ. And then they are very scarce, very expensive, and then you only have small data sets, like points of data. And if you want to to generate data for the whole country or for a whole area, for a whole protected area, for example, you have to interpolate and you have data gaps, and there are a lot of errors. But with satellite data, we can have these consistent measurements that can give you a very good picture of what is going on in your country, what is going on with the natural resources in your countries. So the applications go beyond environmental applications. It has a lot of implications in industry and economy. But we do a lot of environment. We monitor very well. We know how to do that very well with satellite data. But using AI and machine learning, which is actually the basis of remote sensing, we have been processing satellite data using machine learning methodologies from the very beginning. We can also forecast. So using different type of data sets that are not only satellite derived, but model derived, like weather derived parameters, combining that with, for example, estimations of precipitation, estimations of runoff, and different data sets, we can forecast what is going on our planet Earth. In this case, we started monitoring algae blooms. We can do it very well based on the chlorophyll concentration, which is a proxy of algae because all algae have chlorophyll. But then with that information, in addition to all the other data sets that I mentioned that can be derived from satellite data, we can forecast when is that an algae bloom is going to happen. Right now in NASA, we have a new vision, a new strategy that is called Air Action. All the data, which right now, everything that NASA produces is freely available. The main purpose of that data is to have an impact on the ground. And there is a lot of effort in doing research. We have been doing research for the longest, but there are some limited applications on the ground, and in order to keep funding these satellite missions, we need to show that is addressing a need, that is having an impact. And for example, the work that we did in Guatemala, in Lake Atitlan, it's one of the main impacts that it had is that it created wastewater management policies that didn't exist in the country at the moment, but being Lake Atitlan a landmark of the country, for the country, and then visualizing that it was being polluted and that we have algae blooms, it made the government to create some policies and to put them in place to monitor the water of our freshwater bodies. Another cool application, and it's something that are also very involved in terms of satellite data, is monitoring forests. So because we have Landsat, which is a common data set that we use a lot at this type of environmental analysis, something that we are doing is that most of our algorithms relied on time series because we have these consistent measurements that go back to the 70s to today. We have multiple missions that are collecting data with the same exact information. And what that has allowed us is that right now our algorithms is that at the pixel level, at 30 meters, we have the history of the pixel from the 70s to today, and we have observations almost every 12 days. When we combine all the satellite missions, we have observations almost daily, because now it's not only NASA who is producing this type of data. We have the European Space Agency as well, which has a Sentinel-2 through the Copernicus program that produces data very similar to Landsat, and they have 2 missions that are collecting data simultaneously every 5 days, and then you combine that with what Landsat has, which is almost every 12 days. So you have an observation almost daily. And you have that since the 70s to today. So at the pixel level, you have the history of everything that has happened. You can determine actually what is the pattern of that pixel. And what our algorithms are doing right now is that because we know the whole pattern of the pixel, is that we can forecast for, let's say like the last observation was May 1, and we are expecting an observation for May 2nd. We already know, based on the history of the pixel, what should be the value. And if the value is not what we are expecting, something happened. And if the next value, it also differs from the history that we are expecting for that specific date, we know that something has happened. And that's how powerful or how far we have gotten. And I have to say that when I started working on satellite remote sensing, we were working only with one image. And it was like wonderful because we had to actually buy that image. Now we no longer have to buy that image, but just classifying that one image was a big success. And now that's not enough. We had to work with the whole time series of data. And the only way to do that is actually in the cloud. A few years ago, NASA decided to move all the data to the cloud. Today, I think that this year, almost all the legacy data and all the missions that I mentioned there, that have been producing data for over 20 or more years, are moving to the cloud and are there. The challenge that we face as scientists is that, well, we are scientists, we know programming, but not at the scale and efficiency that is needed to solve and to process these big amounts of data. And then imagine everything that can be done. Now we have all the data in the cloud. We can bring different data sets and combine them to have high density of data and derive multiple parameters from it. And that's one of the challenges that I face and that all of my colleagues are facing. So I had to become even a better programmer, even though I'm not precisely a programmer, but I had to learn because that's the state of the art right now. And then something happened. I think it happened almost at the same time that the Lancet archive was open. Google created Google Earth Engine, and that came to change everything. So you know JavaScript, right? Of course, this is a JavaScript event. Well, the first programming language that I learned, it was IDL because we use a lot of MB, and that was the programming, the software that we use to process a lot of data. A lot of the machine learning algorithms that now are available in almost any language, we were doing it a lot in IDL. And then Google Earth Engine came, and we could bring multiple data sets, combine them just in one place, process all that data set, generate at the right parameter. And not only that, we could share our script with other people, and they could comment on that. It was something that, you know, when I started satellite remote sensing and processing data, it was a dream. And even now for NASA, now that NASA has all the data in the cloud, we are using AWS, and almost all the data archives, well, actually all the data archives from NASA are providing cloud computing solutions because the community is not ready yet. So usually the community that I communicate with are remote sensing specialists, and we are not that used at the moment. We are becoming more and more fluent in using the cloud and in programming, but that's not our expertise. We need the expertise that you already have in this field to process this big amount of data. In addition to Lancet, that I have extended a lot because that's what we use a lot for environmental monitoring, things are changing also in air observation, and it's a paradigm shift, as we call it. There are new missions that are about to be launched. One of them is N.A.S.A. Everything that I mentioned for forest monitoring, for water quality, is using optical data. So with optical data, we are working with the optical part of the electromagnetic spectrum. It covers also near-infrared and the short-wave infrared. So when you see a satellite image, usually you understand it because we are collecting data that our eyes understand. But the problem with that data is that if there are clouds, you cannot use it for the purposes that we want to use it, like monitoring what is over the surface of the Earth. For climatologists, they actually use some of that data, but for me that I want to see if the water is polluted or not, if the forest is well, if the cities are growing, or if the crops are healthy, clouds are an issue, are noise for me. But there is a new type of data set that since 2014, actually, the European Space Agency has been providing for free, and it's synthetic aperture radar data. And these are active sensors. Everything that I mentioned before, those are called passive sensors. So what we are measuring is the reflectance from the solar energy, the reflectance of the surface, or the emittance of the surface. So if there are clouds, we are going to be measuring clouds. But for active sensors, the sensor is emitting the signal, and it can go through clouds, and what we are measuring is the energy that goes back to that sensor. So now we can see through clouds. The problem with synthetic aperture radar is that it's a massive data set. Sentinel-1, which is what we have right now since 2014, has available is C-band data. So it's about 5 to 6 centimeters wavelength. we cannot see in that part of the spectrum. The other complication of that is that when you see an image, which actually takes a lot of processing, even the physics of how the data is acquired is very different from optical data. We don't know what we are looking because we don't see in that part of the spectrum. One thing that we realized at NASA was that we didn't have the capabilities and the complete understanding to leverage synthetic aperture radar. So if you want to learn more about synthetic aperture radar, I'd invited you to visit this website. I have the opportunity to lead this effort to create applied content and scripts that are open source to process synthetic aperture radar for biomass estimation and forest monitoring. It's very, very different from optical data. So even though we had been doing satellite remote sensing for many years, then we have a new data set that we didn't know how to process and how to interpret and how to derive parameters from it because the physics are different. And that's from Copernicus. And that C-band has some limitations because everything on the surface of the Earth of about that dimension, 5 to 6 centimeters, is going to be the limit of what that sensor can see. But N.A.S.A is the new mission that NASA is going to launch. It was going to launch in April of this year, but there were some delays. We don't have a new launch date yet, but it's going to be this year. It's L-band. So this is about 25, 26 centimeter wavelength, so it can penetrate further into the canopy. So now with L-band, when we finally have it, we are going to be able to see not only through clouds, but through canopy. This is revolutionizing. But the additional thing for synthetic aperture radar that also makes it very useful but difficult to work with is that the data is massive. When we start working with SAR data, almost like more than 5 years ago, we started working in the cloud, even though the whole community wasn't still in the cloud, because the SAR experts already knew that there was a challenge to work with SAR data. The first year of N.A.S.A, the first year that N.A.S.A starts acquiring data, is going to triple the amount of data that Landsat has acquired since the 70s to today. In 1 day of acquisition at the global scale, there are going to be 30 terabytes of data acquired. This is the only way to process this big amount of data is in the cloud. And the only solutions are that way. So even for us, for remote sensing specialists, when we were used to one image, well, we had to learn how to do all of this in the cloud. So all the presentations that were before me, I was like nodding, like, yes, we need solutions in the cloud because that's the only way to process and generate these products. And it's impossible to do it on premise. There is no computer big enough to do all this analysis. In addition, we are not working only on one-time stamp. We are working with the time series of the data. So we are working with terabytes of data. And how to do that? Well, I have to learn how to. And thank God for Google Earth Engine that allow us to do that based on JavaScript. But we also have our own solutions using AWS. And we can also replicate all of those using Python scripts. This is an image of what I'm trying to explain with SAR and with optical data. So on the right side, you can see a time series using Sentinel-2 with false color combination. This is what happens in the tropics. This is actually an area here in Amazonia, in Brazil. And on the left side, you can see a C-band animation of the same. So the beauty of SAR is that every time that you have an observation, you have useful data. Yes, it does have limitations because of the frequency at which we are working is going to saturate at a certain level. So for tropical forests, maybe it's not going to be able to resolve for everything that is going on the forest because it's going to saturate very easily. But for water mapping, SAR is excellent and is not going to be affected by clouds, and actually for other applications. So one question that we have, and now that we know that we can do this time series analysis, we can leverage the whole archive of information, is where will SAR be more useful? Because it's actually difficult to use, and we have a lot of optical data, and we have so many algorithms that work very, very well with optical data. So one question that we were asking is, where will SAR be more useful? And it's is actually where we have a lot of clouds. So leveraging all the missions from Landsat and the missions from Sentinel-2, we combine all of that data in Google Earth Engine, and at the pixel level, we analyze how many cloud-free observations do we have at that pixel level. And because we can, so we not only did it for one country, but also for the whole pantropical areas, for the whole tropics, and we can see at the pixel level how many cloud-free observations we have. And this is critical for near real-time monitoring, which is something that we do a lot in the air observations. But in addition to that, we can actually get the temporality. We can see, well, what is my maximum waiting period? How long do I have to wait to have a cloud-free observation? And we generated this data set. And in some areas, it can be 4 months without data. Something interesting, and something that I had to praise from Brazil, is that Brazil has the best forest monitoring system in the world, if I can argue. Yeah. They do it through INPE. INPE has been doing this for a long period of time, and other agencies as well. But because they have been doing it for so long, it's documented as well that people know when they are being monitored. So they know that there is a minimum mapping unit. So what they do is that when they know that are using optical sensors, so they know that when there are clouds, no one can see them. So they tend to deforest when it's cloudy. So they already know that. But now with SAR, that's not going to happen because we are going to be able to see through clouds. But using L-band, by the way. If you try to use C-band, there may be some issues. And then in addition to that, because they know what is the minimum mapping unit, which is about 5 hectares, I think, so they start deforesting in smaller patches. And then they do it when it's cloudy. But now we are at a stage in which it doesn't matter, we are going to be able to see it. Eventually, when N.A.S.A. is launched, we are waiting anxiously to be launched. In addition to know like how long do we have to wait, we can also say when do we have to wait. And we also created like the final date of that maximum waiting period. So when I started to do remote sensing, doing this type of analysis, it was a dream. These are terabytes of information. How could I do this? Well, I can do it, and anyone can do it in the cloud. Because all of the data is in the cloud, and through Google Earth Engine, it's so wonderful that we can do this type of analysis that maybe I could just only imagine before. Yeah, now this is playing. In addition to bring all the data, process the data, create a product, I can create an application. I mentioned I'm not a software developer, and I was able to do that. For me, that was also mind-blowing. And there is a new requirement also now if you want to be a scientist and to want to be doing this work, and it's called open science. So everything that we do has to be well documented. It not only ends with publishing a paper and having maybe your name out there, you have to share the script, and you have to show the data. And that requires a lot of expertise, and that's just to show that I am always multitasking, usually. But all of this was done just using Google Earth Engine. So for someone that is not used to do this type of work, that like I'm not a software developer, I could do it all in one place. So that was fascinating for us, and that's what we are doing, and that's what the state of the science is right now. It's not only sufficient to know the physics of how the measurements work, how to derive a parameter from satellite data. We have to create the product, we have to share the script, and we have to visualize the data all in once. And that requires different expertise that maybe we don't have and we have to learn. And when I see this crowd is, well, you have already that expertise. Are you working with satellite data, by the way? Yes? Not that many. Okay, good. So if you are not, I hope that by the end of this presentation, you are enticed enough and excited enough to go to earthdata.gov and start looking for satellite data. So I mentioned about N.A.S.A. That's a new mission that is coming. It's going to be wonderful. We are going to be able to see through clouds. We are going to be able to see through canopy. But there are other missions as well that are coming. Let me see. And now this. So this is the current mission that I'm working right now. It's called Surface Biology and Geology. This is still in planning phase. It hasn't been launched. It will be some years. And I hope it doesn't take that long as N.A.S.A, because N.A.S.A has been in planning for so long. But Surface Biology and Geology mission is an hyperspectral and thermal mission. This is the future of satellite remote sensing. Everything that I mentioned before is multispectral. So we only have like a number of bands. It's about 10 maximum, or about 10, a little bit more. But hyperspectral, these are hundreds of spectral bands. And it means that we have measurements that are continuous, and usually they go from the optical part of the spectrum to the shortwave infrared. And what this is going to allow us is to differentiate at the species level. So right now, with all the data that we have, we can map forests, but even mapping forests is somewhat complicated because forest plantations, for example, look like forests. They are trees as well. So in all the global products that you may see around, and there are so many published right now, there is an issue that forest plantations are also classified as forests, even though they may not be natural forests. So they changed the name to tree cover, and that's why we use cover instead of land use and all those differences. But imagine to be able to see at the species level, to see we have this type of tree. In the water quality application, a clear example of that is that right now we can monitor when there is an algae bloom, but we don't know which species cause that algae bloom. So some species that cause algae bloom can be toxic, but not all of them are toxic. With hyperspectral data, now we can say if an algae bloom is toxic or not, because we can go to the species level. Every component on Earth has a unique spectral signature. And that's the type of information that we are going to get from hyperspectral. So one of the main purposes, actually, the current work that I'm doing with SBG is to create a community of users that is ready to uptake hyperspectral data. And it's a similar challenge that we have with the N.A.S.A and synthetic aperture radar. There is a new data set that has a lot of potential, but maybe the community still doesn't know very well how to use it, how to process it, and how to derive a product. Now we are at the same stage with hyperspectral. And what if I tell you that we already have some precursor data for hyperspectral? Right now, we have 2 sensors on the International Space Station that are capturing SBG-like data. And these are going to be 2 sensors actually in the actual mission, and it is how it is right now. We have EMIT, which is the hyperspectral component, and we have EQUISTRES, which is the thermal component. The thermal component is multispectral, and the other is the hyperspectral component. So this is about 60 meters of spatial resolution, and I mean that at the pixel level. That's what we are looking at the surface. And then we have consecutive observations every 7.5 nanometers that goes from the blue part of the spectrum to the shortwave infrared. And something, if you hear ever hyperspectral, always ask signal-to-noise ratio, because that's a big issue with hyperspectral data. Well, let me tell you, with EMIT, the signal-to-noise ratio is very, very good, because we are capturing very narrow spectral bands. In some of those bands, there is a lot of influence from the atmosphere, and we need a sensitive enough sensor to capture good information. In the past, there had been other hyperspectral sensors. There are also commercial agencies that are collecting hyperspectral data, and that's the issue, that the signal-to-noise ratio is very bad, so you have more noise than signal. And when you try to use the data, you get disappointed. It's like, this doesn't work. I should get a nice spectral signature from my unique component. It's like, you don't get it because it's not good data. But we are at the stage right now where the technology and the engineering has improved enough to have very good data that is hyperspectral. And EMIT is an example of that. So you can go to Air Data and just put EMIT, or just put EMIT N.A.S.A in Google, and you will find more information of this. The main purpose of this mission is to identify the minerals in those clouds. That purpose has been already met, so we could even map what are the minerals in the dust cloud from the Sahara. And now the sensor keeps collecting data, but the orbit of the International Space Station is funky. It's not a polar orbit thing. It's very weird. So the coverage is not that good, but there is already some data that you can use. And in the near future, there is going to be more. For eco-stress, which is the thermal one, we are getting different data products. That is not only for temperature, we can derive temperature from this, but also evapotranspiration and evaporative stress index. The footprint of these images is large, so it's very likely that you will have data, a lot of data for Brazil already. And because this mission, this sensor, has been on the International Space Station for quite some time, since 2018, I think so, there is enough data over there and that you can already play with. And an example of hyperspectral sensor, PACE, is a new mission that NASA launched this year, and this is an hyperspectral sensor already. So this is the future of satellite remote sensing, hyperspectral and synthetic aperture radar. And this is already a hyperspectral. The only issue with this is 1 kilometer spatial resolution, but it's collecting data over land and water. One of the main applications for this is to monitor our oceans. Oceans are huge, so that's why it's 1 kilometer. But all the science that is being generated through PACE is going to be useful for SBG. If you want to look at data that is already hyperspectral and it will have some coverage over the whole world, look at PACE already, because we are already producing data that is hyperspectral. The first light was like 2 weeks ago for PACE. So this is pretty new. So one of the main messages that I want to bring to all of you is that the future of Earth observations is more promising than ever. We have never, ever in our life have had so much data. It's impossible. And as one colleague of mine said, this is the golden age of Earth observation. And what I want to say to you is that you are part of that future, because we need the type of expertise that you have and all the things that you are learning right now to process this data. It's impossible to do it on premise. We need to become very, very well versed on programming languages and multiple open source programming languages to process this amount of data and to create products that are useful for societal benefit. So thank you so much for your time, and let me know if you have any questions. Yeah, thank you. Thanks.